So today we're going to talk about grass waterway design and sorry, I'm a little multitasking here, letting folks in. And just to kind of kick us off, what I'd like to start with is really, first of all, what is the purpose of a grass waterway? I'm going to give you 30 seconds to write down on your own little thing. You can throw them. Actually, no, let's do this. Let's just write them in the chat. Give me, what is the purpose? Why do we put these into a landscape such as this? You can use this kind of as your guidepost of what you might, where this might exist in an agricultural field. You can see two different types of crops being grown here. This is in kind of a little mini valley, so to speak. Nice, dense vegetation there. So throw some things in the chat. Why do we do this? Why do we put these in here to begin with? Awesome. Okay, so Jessica, limit contamination between fields. Okay, that could be really interesting. Is what if you might have like some sort of crop that has specific requirements in another place? There might be GMO kinds of concerns. There might be organic growing one place, a different another place. That's something I hadn't really thought of. Erosion, prevent your erosion, slow down water, exactly, minimize erosion, minimize nutrients, reduce velocities, absolutely. You guys are going so fast that it's making my thing not work. Move surface water through the field without causing erosion. Thanks, Nazreen. That's very thorough. Good job. Basically, everyone's saying limit erosion, minimize sediments. All of those things are really helpful, and that's exactly why we do it. Sorry, my clicker is not working. There we go. Do this one instead. Maybe. There we go. So here's the ones I thought of, and you guys got these first ones. What I put at the top is prevent this rill and gully formation in the uplands. So this is kind of a little more detailed version of how we want to prevent erosion. We're really trying to minimize erosion in two places. In the uplands themselves, before it gets there, we can start to get gully formation. So if you've got a ridge line and then you've got a little valley where that water is funneling in this concentrated area right here, you can start to get gullies forming along that transition of a flat upland and then the slope of that concentrated flow path, right? So we talked about runoff moving through a field or through a landscape, and we've got this sheet flow and it turns into concentrated flow. And if that sheet flow is really long, you're going to start to get concentrated flow, potentially even in the fields. So if you minimize the slope change and you protect those transition areas, you can minimize that gully formation. So it's really, really important further into places like Western Iowa and Kansas and Nebraska, where their soils are a little bit less cohesive and they tend to be more erodible. We're also trying to minimize erosion in the channel itself. So that's what that second one is. These ephemeral channels, they only flow when it rains or maybe during wet periods of the spring when there's lots of rain back to back. Those are the times that we can get erosion and kind of gullying in the channel itself. We're trying to minimize that. And then there's these other pieces about pollution and transport of sediments downstream, but we can also amplify other kinds of ecosystem services in these areas by thinking carefully about the type of vegetation that we provide. So we can provide space for habitat, increased biodiversity. We can even create pollinating plants along edges and places where there's transitions to kind of provide multiple types of services. So this is a great, there's probably others that we can think of, but the big reason we design these and what guides our design is that erosion and sediment control piece. So let's dive in and think about design. So some key design considerations. P.S. All of this stuff is taken from lots and lots of standards and handouts in your textbook. So I've started adding a few more things to Canvas, and all of that stuff should be live and available for you to go and review at your leisure. Really, really encourage you to look through those. This is one of the more, I would say, exciting things that we get to do. We're pulling lots of pieces together in this design, but it's also pretty complicated and there's lots of pieces here. So it's not going to probably stick like glue the first time. So going through it a couple of times is really great. And I think lab tomorrow will be another wonderful way to do that. Okay, so when we're thinking about design, we really want to put where within our site is this gonna be best placed. We need to think about capacity. How do we, this is one of the big tools we're going to do today is capacity of that channel. How big does it need to be to convey, meaning to move through the channel itself, the 10-year 24-hour storm peak flow. Now, this is a design storm, right? We've done this already, but this is a design storm selected by a bunch of professionals who've done this a long time as the most protective of these types of practices in this type of landscape. If you start to work in these kinds of designs, also are really, really prevalent in swales and other kind of connected green infrastructure in cities and along the edges of cities. So the design storm might be different for that. So just pay attention to what the regulations or the guidance document says you're supposed to be designing for. Some other pieces to really pay attention to are confluences. So where does this swale connect to a downstream river or stream or ditch or whatever? Does it have tile that are coming into it as well? Does it have any sort of other concentrated flow paths? Those places where there's connections between different types of flowing water are potentially more susceptible to erosion. There's kind of these points in the river network, if you think about it almost like as a mini river network. Those confluences are places where we may need to add some structural support to minimize erosion. And that can be as simple as some rock or maybe some extra vegetated matting while we wait for that vegetation to get established. The slope is really important. We want to make sure that these slopes aren't super steep. And if there are steep slopes, we may need to put things like check dams or different grade control kind of approaches into them. So we kind of almost have like a stair stepping kind of swale. This is not what we're going to do in this particular version of it, but it's a thing to really pay attention to because sometimes those slopes can get quite steep. And if so, you need to be careful about the type of vegetation you select and also maybe incorporate some other components into the design. Lastly, some things around vegetation. We're going to talk about this briefly today, but it's really important to think about what you select. Is it native? Is it going to be robust and grow into a dense stand in that particular spot? What kind of maintenance are you going to need to do? Maintenance basically means mowing, and how much of that needs to happen and when. And then if there are major sediment supplies within your watershed. So I worked in North Carolina for a long time. And if anybody, I think I mentioned this to y'all about tobacco farms, they tend to be very, very limited in terms of their conservation practices because they're trying to keep the leaves as untouched by residue as possible, let's just say. So the soil is usually quite bare. There's very little support for that soil to stay in place. And so there's lots and lots of erosion coming off of those fields potentially. So if you have a situation where you have a highly erodible soil coming into these, we can pay attention to that. Okay. So those are some design considerations to think about. We're going to address most of these as we go through our design today. I'm going to try and keep a really close eye on the time. There's a lot of stuff to get through here today. Okay. So this design approach is pulled directly from the National Engineering Handbook. Note we will be using the NEH as well as the ASABE standard of practice, as well as some stuff from your textbook. So lots of references to help you get through this particular type of project. I love this set of topics because this is something that if you go into the practicing and consulting space, if you go into regulatory, even if you go into land management in any space, even if you go onto different types of projects, this is something that will come into your professional life on some level. So it's really, really relevant to all kinds of things you'll do in your future career. So love that. So just briefly, I'm not going to read through all of these things. We're going to kind of limit our focus around 1, 2, and 3. These are things that you would do when you do a site assessment, kind of thinking about these components. What we're really focusing on is these middle pieces. How do we design this channel? And what might we do? And then these, like I mentioned about these confluences and transitions, that's what this number 9 is. So you might need additional structures. If you have a lot of flow, that might be off-channel storage, or you might need additional structures to connect this swale or grouse waterway into whatever is moving downstream. So oftentimes, like I said, that could be something as simple as some rock and other kinds of hardening around that transition. The governing equations that we're going to focus on are two. First of all is the continuity equation, basically just flow equals velocity times area. And then we're also going to focus a lot of our attention on the Manning's equation. So Manning's is listed here, and let's step through this really briefly. So velocity is a function of the Manning's roughness coefficient. You guys got a little bit of this last time, I think, from Rose. So just a bit of a refresher. Manning's roughness is tabulated. It is a function of a lot of things, but mostly it's another measure, kind of like curve number, of the channel roughness. And it's really focused on channel flow rather than overland flow. Hydraulic radius, harken back from your fluids classes. This is simply the cross-sectional area. This little figure hopefully is helpful. This blue is your cross-sectional area, and it's in the denominator is the wetted perimeter, this little red line, if you can see that under my cursor. I'm not even sure if you can see my cursor, but either way. So we've got cross-sectional area over wetted perimeter. And this hydraulic radius is going to come back a lot because this is a key design knob that we're going to use as we design our channel. Excuse me. And then lastly, as a piece of this equation is the channel slope. And this is something that you typically get from your topography. You can design this, but often we don't typically change the slope of a swale that much. We just kind of follow the natural topography. So this is what you would do either with a survey. So you might go out and do some surveying and get that actually directly, or this could be done on a desktop approach using topographic data like our USGS maps and those data sets. So a DEM would be a tool that you would use on GIS, something like that. And if you're doing these for longish kinds of runs, that slope is pretty easy to determine on a desktop and then do a field verification. Okay, two governing equations, continuity equation, come back to that. And Manning's equation, also we'll come back to those. This is just listed up here because you can kind of combine these two. And essentially what we're doing here is velocity is what this is written as, and then we're just switching it out to have flow as a function of all of these pieces moving into this version of Manning's. Okay, so a couple things. Oh man, my animations did not work quite correctly. Sorry. I was going to ask you all to think about what Manning's and slope and hydraulic radius would do to velocity in all of these cases. Best laid plans. Anyway, so when Manning's N goes up, so more roughness, more obstruction, if you will, to flow, our velocity is going to go down. And this is pretty clear from the equation itself, right? So if we've got this little equation here, we've got N in the denominator, right? So if N goes up, that denominator gets bigger, that little coefficient gets smaller, and velocity gets smaller. But it makes sense intuitively too. So if we have that velocity being kind of obstructed by grasses and bumpy rocks or anything like that, then that velocity is going to go down. Conversely, if we have a flat slope and then we steepen that gradient and we have a steeper slope, the velocity is going to increase. So we're going to get faster flow moving through steeper slopes. Pretty obvious, but the reason this is really important is as velocities change, those erosive properties of the flow change as well. And so it's a really important thing to consider, and it affects the vegetation and some of the calculations we do as we go forward. Okay, so important piece to note. Hydraulic radius is a little bit trickier. Based on the equation, you can see that the hydraulic radius increase causes velocity to increase. But if you think about it from this little particular graphic, the hydraulic radius is really the ratio of the area to the wetted perimeter. And as that radius gets bigger and bigger and bigger, more of the water is moving through that piece of pie or the little shape of whatever that channel is, and less is in contact with that rough bottom of the channel. And so as your flow area gets bigger and you're tending to, that changes the amount of kind of obstruction or kind of retardants from that channel bed causing friction. So you're just getting kind of more of the water moving through there. Again, a really key piece of our design component that we're going to come back to. Okay, so here's going to be all my annoying little show up things. Those are supposed to disappear, not show up. Either way. So moving on, there's this nice little paper. Oh, that graphic looks pretty blurry, but N is a function of a lot of things. So I just kind of mentioned already that N is a function of vegetation. All the things that you're seeing here, there's really cute, that's terrible, a really cool study showing vegetation effects in ditches. And it's really nice experimental study where they looked at vegetation fully along a channel, only on one side and not, and some really obvious and distinct differences among flow factors there. And it kind of makes sense that this would be really, really, disruptive to flow, high N, and then as you move down, it decreases from there. So the type of vegetation, how dense of a stand it is, how mature it is, how well established, all of those pieces come into the factoring of what that vegetation looks like, or I'm sorry, what that N looks like. Sorry, I was distracted by somebody coming in. Bed material is also really important. And we often get this from surveying the channel itself, or simply deciding based on the soil type. When we're designing a swale, we use the soil type that's there, but this bed material is a really important piece as well. But in these kinds of grass waterways, we have to think a little bit more beyond just the static condition of the channel, because that Manning's N, as I already told you, velocity is changing as a function of these things. Well, the roughness can also change based on a lot of experiments that people have done. It does also changes as a function of velocity and hydraulic radius. So the challenge is, how do we understand Manning's N as a key kind of static parameter in some ways, but really as an actively changing parameter in others, because it's changing as a function of velocity and hydraulic radius. So as that channel, as the flow goes up and that hydraulic radius expands and gets into those potentially vegetated areas or things like that might change, but also it changes simply as a function of the contact of the water with whatever bed material it is, even if it's homogeneous. Okay, so I'm going to show you this graph and then I'm going to pause. So here is what folks have done to really experimentally understand this effect. So we're going to dive into this figure in a little bit, but I want to highlight this a little bit. So we've got many different types of vegetation. Experiments were done to really understand, how does Manning's N right here on our y-axis relate, I think I need to go over here, right here on our y-axis, relate to the product now of velocity and hydraulic radius. So a little complicated, because we now have not just hydraulic radius, which is already a quotient of area to wetted perimeter. Now we're multiplying that by velocity and creating these really complicated relationships and curves. These curves are all taken from the ASAB technical standard on grass waterways. They are available for you to go take a look at. All of that stuff is on Canvas. And each of these lines has been kind of aggregated. It's the best fit of a bunch of experimental data. So little step back, making sure as we think about experimental data that we're really clear about these lines are approximations and best fits to a bunch of data that were collected. Lots and lots of data points on each of these, and they're probably not perfectly on that line, but this is our best guess. And you can imagine that as you get further and further out here, it looks like they're kind of converging and flattening out, and potentially even a little better clarity and precision and agreement in those. And then maybe even up here where we don't know quite as much, we have these really slow velocities, small VR. We tend to see these get a little bit different. They're kind of diverging, and maybe we know a little bit, not quite as precise on our relationship there with Manning. But essentially what this is telling us is that as velocity, let's think about that horizontal piece as just velocity just for a second. As velocities get bigger, Manning's N goes down. So it's kind of like thinking about water moving through that channel. As velocities are moving through, there's more water in the channel and it's less in contact with that rough bed surface. So we're having a potential for that. And we're kind of creating space for that vegetation to also flatten out as that velocity goes up. So we might see more of that effect of a smoothing of the channel surface itself, particularly in this grass waterway condition. This doesn't apply to things like boulder streams because they're not affected by velocity. The key here is that the velocity is changing the way the vegetation behaves. It's standing up and really dense, or it's flattening down when the velocities are flatter. And that's creating a smoother surface for that water to flow through. Okay, those storm flow changes happen during an event, from event to event to event, but we only have one channel that we are designing. We're not designing several channels. We're not designing multiple cases. We need to find a design for a channel that picks the vegetation, sizes the channel itself so that we are able to get water to flow through it, not maximize the size and exponentially increase cost. But we also want to make sure that we're not having velocities that are too fast and they're ripping the vegetation out or they're causing a lot of erosion. Okay, I'm going to stop right there for just a second and see if there are any questions about this particular graphic or any of the things I've said so far. Raise your hand. I can see your little, got everything set up so I can see your screen here of your names and such. So if anyone raises a hand in there, I can grab you or you can put it in the chat. Okay, I guess we're very clear. So we are going to keep going and go on to the next bit. So back to our design approach, really focusing in this little particular spot on how we do this design. We're going to work on peak runoff. We know how to do that. We're going to think about the slope based on our topography, and the big meat of what we're going to do, actually I probably should have highlighted 8 as well, 6, 7, and a little bit of 8 to be able to really design our channel size. Actually should have totally been 8 because that's our capacity piece. I somehow missed that one, sorry. I will fix that. And like I said, this comes from 2 primary sources, our ASABE standard listed here, a little screenshot of grass waterways for runoff control. Also, this is available in Canvas. We're also using part of the engineering field handbook, which is part 650 of the National Engineers Handbook. Lots and lots of stuff in here. I'm not used to talking so much. That is really useful for all kinds of different designs that you're going to do over the course of your career. So this is going to become your very best friend over the next weeks and months, but also probably your career. I love the handbook. There's lots and lots of detail here. It's just a good starting point, however, in many cases, because there's a lot of things that we need to continue to add. For those of you who have never seen technical standards before, I just put this little quote up here because I think it's really helpful to recognize that these aren't pulled out of someone's research lab or something that's just kind of like, oh, I think this is how we should do something. These have been established norms for a long time. Our field is very mature and robust, and it's been lots of good practice has happened over many years. We're still learning new things for sure, but there's a lot of established guidance and technical expertise that go into designing of these practices. In many cases, this has been done for decades, right? And so we're using a lot of the things that's been done in the past. So it's a formal document that is agreed upon by a set of professionals, creating some uniformity to how we do designs so that it's clarity and people are doing it consistently and following best practice, learning from each other rather than just, trying to do their own trial and error as you go along, okay? So important pieces to recognize there. 2 design considerations that we're going to talk about and come back to multiple times today. First off is capacity. We want to make sure that channel is designed enough to create an conveyance for the design peak flow that we are wanting to move through that channel. So we select a design storm. This is usually given to us. And like I said, in the cases of designing a swale, it's a 10-year, 24-hour storm. And then we're just taking the peak flow from that design storm. Okay, so everything we did in the runoff lab is what you do to get from a design storm to a peak flow. So we're not just using the storm or precipitation, right? We're taking that information, going through the TR55 method to get a peak flow. Then we are going to use a bunch of equations that we'll talk about today to figure out channel shape for capacity. The other piece is that we want to make sure it's stable. And we've talked about this, but this is really important to minimize stress on the channel bed. Done a fair bit of work on river design, and we really focus on an allowable shear stress design approach. There's two ways in which you can do the design for this particular type of approach. One is based on the shear stress allowance. I think ASAB calls it attractable shear, something like that. And then there's another one that's a bit different called permissible velocity. And so we are going to use the permissible velocity approach, but recognizing that there's kind of two different pathways you could follow depending on your needs, depending on your expertise, and depending on kind of just your site's erodibility, your soils and things like that. So there's lots of, as you go through this process, you probably even saw this with the TR55, you can define your time of concentration using the lag method or using the velocity method, right? There's multiple ways to do it right. And in this case, there are two ways to really get the stability right. And then we're going to focus on the permissible velocity approach. Okay. So we're going to start. Like I said, we've already know how to do this part. So I'm going to pivot quickly. But just remember, if this is something that was a little, you need a little more help or review on, that's all available to you. And I'm happy to answer questions about that as we go. But we're going to dive in now to the channel shape. And I think Rose talked to you a little bit about the different types of shapes that you can build. And they're listed here on this screen. But essentially, anybody work construction, I can't see your faces or see any hands raising, but if you've ever worked construction, designing a trapezoidal channel is way easier than designing either of these other two shapes, because you can drive a little skid steer or something bigger down the bottom, create a nice flat bottom, and then gently slope the slides up. So that's a pretty easy thing to construct. This bottom one, parabolic, is what we're going to use because it is most similar to a natural channel. And over time, if you build this, what happens is it evolves through stream evolution processes into something that looks like this as well. So we're really going to focus on this parabolic, but recognizing that there's multiple types of channel shapes that you can use. Typically, these are the only ones that are used for grass waterways. However, you can imagine that there's box channels and even circular channels, but we would not use those for a grass waterway design. A little sidebar down here, if you look kind of at this little graphic down here in the bottom, let me turn this over here because I think you can't see my screen now. The challenge with parabolic a little bit is that it's not quite so easy to think about the depth to top width ratio in some ways, because you have this parabola and it has a kind of an equation to describe the curve of that bank. So we also use this other additional piece here, which states that the depth here is a function. It's just a simple, parabola, right? The depth is a function of the top width and then square that bit. So, but K is the thing that we're going to come back to, because this is our design knob that we're going to use moving forward. So K, just to prove to you that this is helpful tool, I just kind of plotted what this looks like. And so as K increases, right, the shape of that parabola goes from a nice flat with a really small K up to a pretty steep side slope when you have an increase in K. So that K is becoming our design, one of our design knobs that we're going to use and try to fit as we go along. All right, I need to get a little quicker here. So the next piece we're going to talk about stability. Like I mentioned before, there's two methods we can use to design our channels. The stress approach, shear stress, is the force of the flow along the bed, such that you're creating a force there that's causing that friction to cause you're causing a force on the bottom of your stream bed, and that is causing instability. So that could make soil erode, that could make plants get ripped out of the stream bed or the swale bottom, etc. We can set that by either one saying, here's the allowable max of shear stress that we're going to see, and that is related to velocity. Both of these are the same thing, essentially. Basically, we're saying we are going to put a speed limit or a cap on how fast water can move through that swale so that we minimize stress on the bed surface. That will keep our vegetation in place, and that will keep our soil in place. So both of these are doing the same thing. We're just trying to keep that velocity to a level that we can account for all of these things and keep it into a space where we have a nice, stable, resilient channel. So in order to do that, we are going to need to select a type of vegetation. And then what we're going to do is really use two conditions to kind of bookend, if you will, the effect of vegetation on stability. So early in the growing season, or after it's been mowed, or even just like right after it's been built, grasses are really short. And so that creates a different kind of retardance class. So remember this graph, I have it coming up in a second. Those curves, each of those vegetation classes are grouped by retardance class. And that basically means the type of category in which the vegetation is acting to slow that water. So it's a little bit like Manning's End, but a little bit different. But that's what we're going to use to be able to kind of understand the effect of vegetation on flow. So short grass condition and long grass condition. Long grass condition can be later in the growing season, later in the life of the swale in general. It really depends on the type of vegetation as well. So looking at this table, this again comes from our standards. We have those retardance classes. I'm going to flip back and forth between these two figures. So back here, this was that graphic I showed you before. We've got the 5 different groupings of vegetation classes, okay? And if you go to this table, it tells you which grouping you are in by the vegetation that you select. Now, unfortunately, this particular table has a lot of grasses in it, has some very ones you'll probably remember or have recognized. Bermuda grass, pretty common. Kudzu, really interesting and awful, particularly awful, viney plant that was brought over to this country for erosion control purposes and has since taken over much of the southeastern United States, particularly their ditches. So if you ever drive down South Carolina, Georgia, any of those places, even North Carolina, you'll see whole stands of forest kind of enveloped into this particular messy plant. Anyway, hence the name, very dense growth. A challenge for us in Iowa is that the NRCS recommended grasses are not on this list, but I've given you a document that has them and the retardant classes that they should use for those particular things. So the thing to notice from this, I think that's kind of just helpful, is to recognize that, again, we've got these retardance classes over here, A, here, at the top. That means our Manning's End is high. So Manning's End high means our resistance to flow is high, which means our velocities go down. If you just think of it without the effect, right, broadly, just the equation itself. So this is that really excellent stand, dense growth of dense growth of kudzu, really dense, tall Bermuda grass, high retardance class. And then now as we go down here, short grasses. So you can come down here to the Bermuda grass at the bottom, still good stand, but cut super short, just a few centimeters, or even burned. Sometimes we might burn grasses for prairie management, etc. So that would be all the way down here into the class E. So the retardance class is going to give us what's called this retardance curve index, which we use here. And these guys are then into this lovely little equation. So we can use the equation instead of kind of reading it off this curve, which is super helpful because this is all going to be done in Excel, where we're going to use a lot of tools that we've already practiced, such as GoalSeek, designing a spreadsheet to be really easy to follow, etc. Okay. Like I said before, these this particular table has several of the things that we are going to use in this class, but again, our grasses are not listed here. But a couple of things I want to draw your attention to. So the first part of this reference stem density and this cover factor, these two columns are used if you use the tractive stress approach. So we aren't going to use those, but it's really helpful to kind of ground truth and like intuitively look at this table. So at the top, you see stem density. I think stem density is an easy one to think about. Lots of stems mean more dense coverage, right? And as you go down, it gets less. The table in the book doesn't have these little blue lines. I added them because it's a very weird table to look at. I kind of want to walk you through it before we go too far. Basically what it means, so this second group right here, oh, sorry, I'll come over here again. Sorry, the second group here, this Bermuda grass to bluegrass, blah, 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 has these specific stem densities, and these are specific to those different vegetation species, right? As you go over in this half of the graph, this is something I recently learned, so it's kind of wild to me that this is written this way, but it is what it is. This is how you read for all of these grasses on a 0 to 5% slope. Your erosion resistant soil has a permissible velocity factor of 2.1. And then over here, it's 1.5. And that is for all of these grasses for that particular slope. Same for 5 to 10, over 10, etc. So a little tricky. You probably can't read all of the bits on this on your screen. Maybe you can. There's some interesting footnotes down here. I suggest you you read some of these, particularly 3 and 4, which talk about steep slopes and excessive velocities. So being really careful about when you get into steeply sloping terrain that we might need to do things like create a step change or some sort of transition support around that particular spot. Okay. Okay, with that, we're going to keep going. So in our permissible velocity approach, we're going to design for these two end member cases, short grass, tall grass. So for capacity, we are going to design it such that it's big enough to carry the peak flow when the grass is really long. So that suggests that we need to think about how can that, we're going to kind of, in some ways, constrict the amount of available flow because we've got a lot of vegetation growing up into our channel. So we might need the channel a little bit bigger once that grass is long so that that flow can get through. But we also have the fact that we can see some flattening of the grass if the flow is really, really fast. So thinking about big enough channel, we have long grass. Stability, this is when the channel is really short. So, or I'm sorry, when the grass is really short. So we want the velocity slow enough. So when the grass is really short, we have less resistance to flow. And we want to make sure that that velocity doesn't go ripping through there and all of our vegetation gets pulled out, or we get sediment loss and erosion of our channel bottom. So in that case, that is really related, and we're going to use hydraulic radius as our design tool there. Okay, so this is our kind of big picture, what we're hoping to accomplish today. So as you can imagine, lots of things interrelated. I've already told you how that graph showing retardance class curves, how Manning's N was related to V and R. So it requires a bit of some iteration to be able to do this well. So to do this design, we're going to start with our stability condition first. So on that first graph, we've been talking about capacity because that's where our peak flow is. That's all that stuff. And then stability, we're going to flip it in our design and start with our stability condition first. We're going to pick a retardance class from our vegetation. We're going to use the permissible velocity approach to find a suitable channel geometry. Then we're going to use that channel geometry, make it just a little bit bigger, right? Because we've got vegetation growing up and creating extra flow obstructions so that we can create a little bit wider. And we're going to check things all along the way to make sure we are meeting our stability conditions. Okay, let's dive in. We have about 10 minutes. It might take you a little longer just to make sure we can get through all of these things. So stability condition using the short grass condition. So what our end goal is determine that hydraulic radius R. The first thing we're going to do, select our retardance class and the permissible velocity from those tables that I just showed you. Tables 1 and 2 and that curve, those curves, right? So we're going to do that from those tables. We're going to create a guess at that hydraulic radius. It might sound a little bit wild, but we're going to first just start with a guess of hydraulic radius. Every time we do these kind of iterative, we have to start somewhere. And if you go back to kind of your memory banks when we did this before, your initial guess, particularly if you're using Goal Seek or Solver in Excel, is really important. So we'll talk about that in lab tomorrow about how do we pick a good starting point. Okay, the next bit is going through these 3 steps. So we're going to compute the permissible velocity times R. That's permissible velocity from that table, and the hydraulic radius we just picked. Then we're going to either compute or look it up on that figure 1 for our short grass retardance class. That's just that figure. And go back, maybe this guy. So first off, we're going to pick our type of retardance class. Our permissible velocity we pick from here. Note a soil erosion. We can get this from the Web Soil Survey. Rose will go over that a little bit more tomorrow, but essentially this is something that we know. We can pick this from our soil type. Okay. So we've got permissible velocity from a table. We've guessed R. We can calculate N now from that curve in figure 1. Then we go back and we calculate using Manning's to get velocity. If we did this perfectly, permissible velocity would equal our Manning's and we'd be good to go. But it's really challenging to do so. So what we do is we change R using Goal Seek, Solver, etc. We can do it iteratively, manually, I suppose, but this is much more efficient. There's one step. The outcome for this is to decide on an R that ensures channel stability. Okay, let's recap so far, maybe. There we go. Now we have R, area and wetted perimeter, that ensures stability. But we don't have an actual channel geometry yet. We just have the R, the ratio of A to P. So we need to figure that out. How do we do that? Oh, hey, look at that little equation. Let me just throw all these in here. I'm not sure why they did that funny little bit. Okay, so now we're going to determine the channel geometry. And this stepwise stuff I'm showing you here is for a parabolic shaped channel. Your textbook does it for a trapezoidal channel. So we have both. If you want to go back and look at that, we're going to use a parabolic channel for lab. So this one is the one I would suggest you follow along with first. Okay, so like any other iterative solution, we got to start somewhere. So we're going to guess a depth to start. That's just to get us started. And then we're going to calculate the top width from our continuity. So we've got velocity. We just calculated from Manning's before. And we've got our peak flow from our design storm. We go 10-year, 24-hour storm, TR55, blah, 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 Q peak. That Q peak comes in right here. Okay. Now we can compute R from that top width and our depth. And again, we're probably not perfectly great because now we've got this continuity version. We're calling it continuity because we're starting with our continuity equation, but this is just where we're trying to get the channel geometry right. So we're basically selecting a D and a T. Remember, depth, top width, channel, top width, and then the depth. Another iteration to change depth to get those two equal to each other. And the outcome, rather than, so what we're going to do is for this parabolic channel, once we've gotten D, we're going to use this K and take that forward. That's the thing we're going to use. Okay. So just to recap again, we have R from the first step based on our area and perimeter, wetted perimeter. That makes our channel stable when grasses are short and velocities are really fast. Now we just basically take that R, which is area over P, and try using the continuity equation, get a shape that allows that peak flow to make sense. So all that second step did was simply take R, which is area over wetted perimeter, turn it into a K, basically a shape of that parabola. So doing just a little bit of geometry to get that right. What we don't know is now we just need to ensure that we have capacity through that channel to convey our peak flow. When the vegetation is a bit longer, flow resistance is greater, and our velocities tend to slow down a little bit more. So we end up getting a bit more flow through that channel then. Okay, so this next bit is the conveyance component. This is step 2 or part 2, using the long grass condition. So the first step, again, we've already got 2 goal seeks. Now we're going to get a third one. So lots and lots of fancy excelling, if you will. So to start this one, we're going to guess, take our channel dimensions, and we're going to start our initial guess with one of these parameters. You can guess top width or depth, either one, and then you calculate the other one from the K. But we're going to guess a little bit deeper or a little bit wider than what we determined from the first part. Then you're going to calculate your area and your hydraulic radius from those new dimensions that you just guessed. Just a little bit bigger, right? We're just increasing it, stretching it just a little bit. Again, calculate the continuity velocity from Q equals VA. Compute N for the long grass retardance case, all the way back to that figure 1, and those equations that are in that. Now we've got a velocity from the continuity. Now we got a new N because we had that little curve, right? We're going to go back and calculate the Manning's velocity. And you probably predicted this already. Another lovely goal seek to make sure these things agree. So our continuity, we determine that one, V continuity, by making our channel a little bit bigger to accommodate this long grass condition. And we then calculate Manning's flow. We're trying to make sure that those two equal. Probably not going to be perfect the first time, so we'll use goal seek again to get those to be right. So we're trying to just enhance our channel size a tiny bit. So the outcome in this case is that now our channel dimensions are such that we are stable, because we did that to part 1. Short grass condition ensures stability. Also gives us the shape because we turn the R from the short grass condition approach into some channel geometry, namely K, which we can then calculate D and T from. And then we also increase the capacity just a bit to make sure that we are able to convey the flow when the vegetation gets long and dense and we have a little bit more flow constriction. Now, small things to consider. We don't ever do anything in engineering often without some sort of measure of safety, just to kind of cover our butts, so to speak. And so typically our final design will include a 20% freeboard. So if you go back to, let me see if I can find that channel shape here. What that basically means is that instead, I'll look at this parabola one, instead of this little t, we're going to have this top T here. And don't worry about these equations over here on the side, but basically what we're saying is that this top width is giving us a factor of safety of 20%. So essentially to do that, you use your depth and you calculate a new capital D using that 20% correction. And then you can calculate your new capital T top width from the K and the designed freeboard added D. Another check is, as you're going, you want to make sure that your channel geometry didn't get really wonky and you have like a really narrow and deep channel, for example. So you want those side slopes to be nice and gentle, such that your flow off your fields doesn't come into a really steep slope and cause erosion, right? And so a good rule of thumb or a good rule of practice is around a 4:1 horizontal to vertical. So wide horizontal, shallow vertical. And that 4:1 is a good rule of practice. And for parabolic channel, that corresponds to that value. Okay, I went right up until the time, and I'm going to stop recording really quickly.